Thank you. Thanks. It's great to be here again. This is some work. Actually, most of it I did when I was at UBC. Adam Monahan's in actually an atmospheric scientist at University of Victoria. Will Thompson, a former student, and even talk about some work from some years ago with my postdoc supervisor, Joe Keller, which has come up again. So basically, the motivation for this talk is sort of the observation in a lot of either climate data or environmental type data or other actually applications that where rare events actually aren't that rare. So what we would call Pareto type distributions or distributions with power law tails. So they're not normally distribution, but you have essentially what are called heavy tails or fat tails. And so these are just a couple of graphs showing that. So this is one example of the darker regions are showing where there are more of these intense events of what we would think are rainfall events that are more intense, but they're happening with not just a normal distribution. And this is a log plot of distribution for some financial fluctuations. And again, this on a log plot, normal distribution looks like just this parabola, but the fat tail distribution will have this these fatter tails. So we see this in a lot of different data. And of course, this sort of stuff also comes up whenever we have some sort of nonlinear feedback. And a couple of simple examples within the, let's say, temperature, greenhouse gas feedback areas. You know, first of all, noting that if we have a distribution of noise that's Gaussian but nonlinear feedback, that can automatically give us these sort of fat tails. But also we see that with different types of timescales involved. This is different relaxations of temperature in some of these feedback models. In particular, I'm going to be motivated by looking at something called correlated, additive, and multiplicative noise. And that's been studied in quite a number of models, again, in the atmospheric and ocean coupling type areas. Essentially, the idea is, as you can see from this example, we have a variable x. X you can think of as some sort of fluctuation around some mean state. And eta 1 and eta 2 here are two different noise sources. And the point here is that eta 2 in particular, all the coefficients here besides x are just constants. So this is additive, but also multiplicative noise with eta 2. And since eta 2 is the same for both of these, we have correlations between the additive and multiplicative noise. And so I'll say a little bit more about how these things show up, but the point is the steady state distribution for this process has this power law. Here we have x to a power law tails that shows up. And so this has been studied in quite a number of different scenarios in studying atmospheric ocean climate modeling. And in particular, being interested in if we think about these x's as fluctuations around the mean, things like the skewness, the fat tails, other sorts of asymmetries. And maybe I'll just say that, you know, how these things generally come about. We typically have large PDE systems for which some sort of mean state is identified. And then this x is typically this fluctuation, you know, and boiling it down to the simple time dependence involves some sort of projection onto certain types of modes, in particular the slow components in those systems. So this is quite a large reduction from large PDE models. But today we'll just focus mainly on time dependence. But within that, the question is, why is this fat tail behavior actually showing up in so many of these different sorts of data or models? And in particular for the climate systems, we typically have things evolving on different scales. So I have x, y, and z here, so you can think of them evolving on, let's say, over centuries or days or years. So you have all different time scales going on. And so the idea is that the faster scales here represented by y and z, we're somehow looking at some mean fluctuation for those around some mean fluctuation around a mean state, and these are some nonlinear models. So there's that sort of approximation with this projection. So we're boiling that down to this CAM noise process, which I'll now call Y from now on, with this, again, multiplicative and additive noise correlated. And then that will be feeding in, this Y process will be feeding into our slow process X. So you can think of that as the decades or century evolution over a long time scale. And so the question is, how does this sort of CAM noise with these fat tails influence this long time scale dynamic? Another, sort of piece in this puzzle or question, part of the question is also noticing that in also looking at proxy data from things like ice cores or other sorts of proxy data, there's been a number of statistical analyses also looking at that. So after you detrend the data and look at the statistics of that, they also recognize these fat tail statistics, sometimes called Levy noise or alpha stable processes, and I'll define those in a minute. But the key is here is finding that alpha, which is an important parameter in this problem, is less than 2, which essentially says we have fat tails, and we'll see exactly how that's defined in a minute. But so again, the question is, why would we expect this type of fat tail distribution to show up in this type of long timescale sort of data? So before getting into exactly how these things all fit together, I'll just give a little review of what an alpha stable process is. So, so alpha stable processes are basically are distributions with these power law tails, and there's this exponent alpha, usually written in this form for the density. I don't generally have closed form for densities. Cauchy distribution is one exception to that. But in general, these processes are defined in terms of in terms of characteristic functions. And so we see here we have this parameter alpha, which describes the power law tail, but we also have a beta and a sigma. Beta is basically giving us asymmetry, and sigma is like a scale factor to see how big the fluctuations are. And so we compare time series of, let's say, Brownian time steps versus, or Brownian increments versus Cauchy increments. Hopefully you can see the difference between these behaviors. So a Brownian is sort of typical Brownian fluctuation. But the Cauchy case looks sort of Brownian, and then it has a big jump, and then it looks sort of Brownian and has a big jump. And in fact, these Levy distributions can be modeled by a combination of Brownian motion with jumps. And so that sort of characterizes these fat-tailed distributions. And that will be a little bit important a little bit later on when we think about those. But basically, important thing is this writing thing in terms of the characteristic functions, and then thinking about how we deal with these power law tails. In particular, notice when alpha is less than 2, as I mentioned, that's a critical case for us. If I try to, for example, compute the variance, it doesn't exist. And if alpha is small enough, even the mean doesn't exist. So these are going to behave very different from a normal distribution. And in fact, even though we know a lot about these processes, even some, what we might think is sort of basic key points haven't been really studied till recently, or relatively recently. So for example, these alpha stable processes, they're called alpha stable because they actually come out of a generalized central limit theorem. And basically what that is saying is if we have a bunch of random variables that have this power law behavior in the tails, I look at a sum of IID random variables of that type, and I normalize that sum, let n go to infinity, I'll actually have a convergence to an alpha stable process. And but that convergence rate, it actually varies with the exponent. And so here's just a graph of that. So this big dip here where the exponent goes to 0, so that's basically saying very slow convergence. So I mean, I need a lot of these to actually get a convergence to an alpha stable distribution. That's right at this critical value of 2, where we go from this sort of power law tail behavior to a faster behavior, which sums of these will then converge actually to normal distribution. So alpha 2 is basically cut off between the usual central limit theorem and this generalized one. And so, these sums will actually show up as we look at this, long series of data and averages of those. Okay, and I'll just mention here how we get this this convergence rate. I don't really want to go through these details very much, but again, just to say the characteristic function, again, is very important. Characteristic function is the Fourier transform of the density, right? So if I have the sum of a random variables, and I take the characteristic function, well, this is just in the exponent, so that will turn into a product. So I can look at the characteristic of the sum. It's going to be the characteristic of an individual scaled by the scale factor. So that actually allows us to use essentially an asymptotic expansion in n to get the behavior of the characteristic function for the sum. And it turns out it has a form that's similar to the usual characteristic function. So that's just the usual thing in this green and red boxes. And then there's a correction from which we basically get things that behave like 1 over n, and that gives us a convergence rate. So I just wanted to mention that because this form will show up again as we look at these more complex processes. Okay, so we've had a little review of alpha stable processes, but as we saw earlier, the type of process that shows up is this CAM noise, with this correlated, additive, and multiplicative noise. So we're going to do some sort of bridge between this CAM noise and our alpha stable process, and then think in terms of this multiple timescale framework and do some sort of averaging over these different timescales. But we can't use the usual Gaussian averaging because we don't have Gaussian random variables. But so we'll review some of that Gaussian averaging and see how we can actually use it in this alpha stable situation, and then from that bridge over to CAM noise. Okay, so that seems like a lot of work. So before doing that, do we really actually care about this CAM noise? Because, I mean, did it just show up in like one particular case? You know, why are we working so hard for this one particular case? And in fact, it's more prevalent than you might imagine. In fact, after looking at this, I realized I've encountered this in a number of different stochastic settings without really paying attention to it. So let me give you a little sense of that. So for example, this is one of the simple sea surface temperature models studied by Sura and company. And essentially the main idea is we have an equation for the evolution of the temperature and then some flux that's a nonlinear function. And so we look at some mean temperature with some fluctuation. And we think about this flux as being some mean value with some random fluctuations. Now, you can go through a number of expansions, putting these in, counting these fluctuations as small or whatever, and using certain functional forms motivated physically, you end up with this equation for the fluctuations in temperature. And if I think about this f prime as the random part, I have a random term here that's additive. I have another random term over here, oh, sorry, here, that's multiplying my, my fluctuation for t. So this is, again, our additive and multiplicative noise correlated because they both have an f prime. So it just comes out of sort of a usual expansion. And this is just another simple example to show more or less the same thing, but totally different setting. This is basically a damped oscillator model used for machine tool position and machine tool cutting with some nonlinear force. This has an equilibrium, some non-zero equilibrium in terms of this force. But if we have this k being our material parameters with some uncertainty eta or some noise, then we can go ahead and do this sort of similar type of approximation where I look at fluctuations around this equilibrium value. And the equation for that fluctuation x is, again, the linear part, but now we have the nonlinear part. And again, we get an additive piece and a multiplicative piece as well, coming out of the fluctuations in the material parameters. Again, just a expansion for, let's say, small x and noise.
What do you get from this situation?
Sorry, what do you get?
Yeah.
Well, here I get the behavior of the fluctuations around the mean. So for example, in the machine tool problem, you care about that because you'd like to do a nice smooth cut. But if you have big fluctuations around that, then you're going to get not such a smooth cut anymore. So typically, you want to know, like, am I hanging around the mean or am I fluctuating a lot? And so this is giving you the stochastic behavior of those fluctuations. And similarly, in the sea surface temperature, you want to know, like, or rainfall, models like that as well. Am I going to get very large rainfall events, or am I going to stay close to the mean?
It depends on what basic equations.
It depends on these random fluctuations, right? So you have random fluctuations in the material parameters, and it also depends on, you have other coefficients that describe the material parameters here, as well as the nonlinearities.
And for these parameters,
Yes?
what is the boundary between good behavior and bad behavior?
Well, here, good behavior is x is 0. And
No, not in terms of x, but in terms of parameters of the equation.
oh, okay. So for the noise, typically the error in the machine tool problem, it's a few %. And these parameters have physical ranges. Yeah, I don't exactly know for this particular C, but yeah. So we have those from experiments. Okay. Okay. So so this is basically just to say that so doing this sort of expansion, expanding around a mean, looking at the equations for the fluctuations, but keeping these random fluctuations in the equation, it's quite generic to actually get both multiplicative and additive noise as correlated. So we're essentially replacing these fast fluctuations with a fast cam noise, but we actually want to know how those fast fluctuations are going to drive the long time behavior. Okay, and that basically is telling us why these fat-tailed distributions can be showing up in the noisy data. So really, we want to know, can we somehow, we'd like to use something that we know about alpha stable forcing. We know more about alpha stable behavior than cam noise, and the question is, can we somehow use that to approximate the slow time behavior? Okay, so we know that cam noise is showing up, so now let's look at this averaging for the non-Gaussian case. Okay, because essentially, instead of solving some large system, I want to sort of reduce things down to just looking at the slow time, long time behavior. Okay, so to do that, let me review some of the basics of averaging in the Gaussian case, and then we'll see what carries over, what doesn't carry over to the non-Gaussian case. So this is sort of your classical system with x is your slow variable here. There's an epsilon small parameter here that says if epsilon is small, then y is going to fluctuate fast compared to x. And instead of using, eventually we'll do dl, which are these Levy increments with this alpha stable process. I'll replace that right now just with Gaussian noise, Brownian motion for the moment. Now, if we just look at the average deterministic system, what is the usual approximation? The usual approximation says, well, if y is fast, then x looks like a constant compared to y. So I'll actually use the conditional probability of y given x. Okay, so I fix my slow variable x, and I average over this conditional density of y given x. And if I do that, then I average out the y, and I get some new averaged version of my function here, f, which is just f bar. So that gives me my typical average deterministic system. But in general, we don't just want a deterministic system. We also want to capture fluctuations as well. So sort of the proper way to derive this using infinitesimal generators or PDEs that describe stochastic differential equations is to take our fast, slow system here. Now, since this is basically just a system of stochastic differential equations, I can write down the PDE for the expected value of some test function of x and y, p. So we know the form of that. It's just a second order differential equation, partial differential equation, including time. But of course, it involves epsilon because we have slow, fast systems. So in fact, we can solve this with a perturbation expansion, really a multiple scale type perturbation expansion. And as is typical for those sorts of expansions, getting the equation for the correction to the leading order turns into a solvability condition on a PDE acting on the V naught here, the primary variable. So that solvability condition really is equivalent to taking an average with respect to this conditional density. And that really just follows from the form of this operator. So this is a well-known approach. The important piece is that after we do this projection, we get, or averaging, we get a new averaged equation. And from that averaged equation, we can read off the equivalent stochastic differential equation. Okay, so it's like taking stochastic differential equations, writing down the equivalent PDE, getting an average PDE, and then writing down the equivalent stochastic differential equation for the average PDE. And that has the form of, here's our F bar, that's our average drift that we had before. And then we have a fluctuation term. The circle is basically corresponding to Stoyanovich interpretation of the stochastic integral. And sigma, it comes out of the properties of these coefficients. So all of the F and the G and the coefficients of the noise are encoded into the sigma. So that gives us an averaged, but still stochastic, but averaged equation for the slow dynamics. And so these fluctuations essentially are capturing the same type of fluctuations we would have if we looked at the system on a long time scale. Okay, so that's the usual sort of derivation, but maybe a slightly more physically intuitive way to see this is, again, to take our average system, to look at fluctuations around the mean, thinking of these fluctuations as somehow small, and doing an expansion of our equation here for x. And so we get an f prime here, and that's really sort of the usual drift that we have in the average case. And then we get some additional fluctuations or an error from doing this type of expansion around the mean. And the real question is, how do I actually approximate these additional variations or fluctuations with some noise process? And that's essentially what this term that we saw in the previous slide comes from. But another way we can actually get this result is that the sigma is really just the integral of the autocorrelation function of these fluctuations, right? So these fluctuations are all in terms of the mean and our x and y and so on. So we can write this down, take the conditional expectation of those fluctuations, and that will really give us a sigma. Okay, so that's just some more back of the envelope way to get this result. But this is important because this basically says somehow I need to be able to compute the autocorrelations. So when I go to looking at this process with a Levy term or an alpha stable term, right? So this is, again, this increment now has these power law tails, but I'm still in my slow fast system. Similarly, I could write this down with, instead of alpha stable, I could write it with cam noise as well, but let's stick with alpha stable for the moment. The problem is, you know, I need to write down the autocorrelation function if I'm going to use my Gaussian averaging. But I don't have autocorrelation functions, right? Because this power law tail, as we mentioned before, I don't have variances, I don't have second moments, so I don't have autocorrelation functions. So I can't use this usual Gaussian averaging approach to derive a stochastic average equation for this process, to approximate the slow process. But I do have my characteristic functions. And so actually the way we'll go about this is go into Fourier space and calculate an average process in Fourier space. Okay, so we have our alpha stable process here. Instead of Gaussian increments, now we have these Levy increments, or which have these power law tails on the fast variable. And And for this process, of course, we can again write down an operator, in this case, a forward Kolmogorov operator. So it has not your typical diffusion term here because of the type of noise that we have. But really, it's valuable to work with these in this Fourier space. So I basically look at the Fourier transform of this. So I'm really looking at the equation for the characteristic function. And of course, this still involves my x and a y, but then in terms of other variables. And in fact, I'm going to look at a particular functional form of f and g just to make sure things come out nicely, but we can look at more general functions as well. But the point is we have this expression for the characteristic function. So really, this is going to be in terms of the characteristic variables, or the Fourier variables m and l. And then from there, what I really want is the behavior on the slow time scale. So somehow I want to read off the slow behavior from here. So I want to find the piece in this equation that corresponds to the slow time behavior. And so I can look at the asymptotic evaluation of this characteristic function on short time and long time. I'm really going to concentrate on long time because I'm looking at the slow variation. And if I look at the exponents of that characteristic function, I actually see that this form corresponds exactly to the same form as I would have if I just had a Levy-Brownian motion. Basically, instead of Brownian motion, I have a process driven by Levy increments. And from there, with a particular coefficient sigma, I can then read off that coefficient sigma and compare it to my exponents here. So by looking at the long time behavior of the characteristic function, I will be able to write down what is the fluctuations that I need to put in my slow approximation, my averaged approximation to x, based on the fluctuations in the fast variable. Okay. Okay, so here's just an example from the linear case. Now, the linear case is kind of trivial because if it's linear, then we can actually write down everything exactly just by linear transformations. But if we use this averaging approximation, here's my full system with some constant coefficients and linear in x and y. And I go through this averaging and read off what I need from this exponent. And that exactly tells me what my coefficient will be for this Levy process. And of course, this depends on the various a's and b's and coefficients I have in the original process. Okay. And here's just a comparison just to show for the linear case. So this is a comparison of the density of x from the simulation of the full multi-scale system versus the similar fluctuation, but just using the averaged equation. So they sit pretty much on top of each other. Notice my alphas here. Remember, alpha less than 2 is this fat tail case. So here, alpha is less than 2 for all of these. The beta here is non-zero. So this is the asymmetric case. This is the symmetric case. And also, maybe you can notice that the fluctuations in the tail here are a little bit more, especially when we get closer to alphas near 2. And if you remember, our convergence to this generalized central limit theorem was very slow in terms of number of terms we have to get this generalized central limit theorem. So this is basically saying we have to really take a lot of numerical simulations in order to get really nice smooth tails. And that's typical if alpha is close to 2. Okay, just maybe a couple of technical comments on the nonlinear case. So I showed you the linear case. The nonlinear case is a little messier. Probably the main thing to say here is, you know, we went into Fourier space and then we read off some coefficients in the exponents. In the nonlinear case, things are a little bit more ambiguous. And so it was actually useful to use a transformation, not to work directly in the variable x, but transform our functions so that basically what it gives us is the fluctuations in our approximation to x are somehow parallel to the equation for y. And that helps us to separate terms better in this in this Fourier space. But of course, when we do that, we have to work our way back after reading off these coefficients in the exponents for the characteristic function for the fluctuations. So we read off these coefficients, and we have things in terms of our transform variable, but we have to get back to x. But since we got these coefficients from, basically this is the form for the Levy distributions, there are jumps, okay? And so when we're doing these transforms back, we have to actually calculate, account for all of these jumps. And that essentially leads us to what's called the Marcus stochastic integral, which is like the Levy or the alpha stable equivalent of the Stochanovich integral. So incorporating jumps for noise that is not just additive, but actually dependent on states, a state-dependent noise. And so this is just the various pieces that have to go into this calculating the jumps and so on. And you'll notice these thetas here. And what the thetas are really doing there is that's part of the definition of the Marcus stochastic integral, which is in the fluctuations that we have in this averaged system in the nonlinear case. And what that basically says is the way that this integral is defined, it's in terms of a bunch of jumps and then this variable theta, which is sort of like this variable that's traveling in between and connecting the jumps and being more or less dictated by the behavior of this term. The nice thing about that interpretation, it also gives us a nice way to actually simulate these results. So even when we come down to this reduced system, we still have to do some sort of simulation. And so we have relatively efficient ways to do those simulations. So we, again, can go from this larger system with fast and slow variables, typically much more expensive to simulate because you have to refine both the fast scales and the slow scales, to just computing on the slow scale. So that's a much more efficient calculation. And here again, we just have the comparison. So the red and the blue are the fully nonlinear full system and the nonlinear average case, so they agree well. The green is actually if we use the linearized version as an approximation. So as you might guess, we don't resolve the tails in that case, but we really resolve just kind of the center of the distribution. And this again is using this Marcus stochastic integral in the simulations. And we have a few different examples of types of nonlinearities that show up in different scenarios. Okay, and besides just, this is again the densities for X in both the full system and the average system. Besides just thinking about densities, we also were interested in quantities that characterize time-like behavior. So typically you would look at that by looking at an autocovariance. So for example, if you had an Ornstein-Uhlenbeck process, just a linear stochastic process, then your autocovariance would be exponentially decaying. So if you put it on a log plot, it will just be linear, as these green stars are here. But of course, in the nonlinear case, you'd have some nonlinear behavior. So this is, again, comparing. In this case, again, we don't have an autocovariance because we don't have a second moment, but there's a equivalent sort of quantity to autocodifference for processes with jumps. And so we see this nonlinear behavior. This is for the full system versus the average system in the nonlinear case. If we keep only the linear terms, just as we missed in the tails, we just get this linear part. But this at least tells us that using this nonlinear approximation, we do well capturing this time-like autocodifference behavior as well. Okay, so so we've talked about going from this usual Gaussian averaging, which lets us go across these different scales. And we've talked about the prevalence of cam noise. And we've even derived a result for doing a non-Gaussian averaging when we have alpha stable processes. But we wanted to do this for cam noise, right? So we haven't really done that for cam noise. So what is really the connection between cam noise and alpha stable? They're not the same. Cam noise has a power law tail, but it's certainly not an alpha stable process. So the question is, under what circumstances would we actually expect the cam noise process to somehow give us this alpha stable like behavior? And as if you remember back to some of the climate examples, we were seeing that power law tail in these long time statistics. So we expect somehow the alpha stable process should be in there, even though the derivation, the reduction of the equation gives us this cam noise process. Okay, so yeah, so this is just this equation again. So we're basically saying I reduce my fast fluctuations into some cam noise process with this correlated, additive, and multiplicative noise, not necessarily alpha stable. And how do I turn that into stochastic averaging result that I can compute efficiently on this long time scale? Okay, and so now our multiple scale system is really, our slow variable is still x. It's being driven by y, but the y is this cam noise process now. Okay, and so the key here is being able to say, can we somehow connect this cam noise process here with what's called an Ornstein-Uhlenbeck-Levy process? So Ornstein-Uhlenbeck would be just a linear equation in Z here, linear drift and additive Brownian motion white noise. But instead we have this Levy process instead of the Brownian motion. Okay? And we're going to, instead of just comparing the processes themselves, we're going to look at the integral of these processes, and we'll see why that's valuable as we go along. But one hint already is we want to use this generalized central limit theorem. So if we want to use a general centralized limit theorem, we should have a sum of random variables. So somehow we'd like to write the integral of this cam noise as a sum of random variables. But remember, the generalized central limit theorem basically relies on the fact that, for example, a sum of random variables R, they have to have IID distributions. Okay? And so if we had a sum of our IID, then we could say, okay, I have an integral of my y, even though it's cam noise. Once I integrate it, I'm summing. I use the generalized central limit theorem. I'm back to alpha stable process. And then I can use all the averaging results that I derived for the Levy process. And basically that's, again, because just to remind you, the cam noise process has power law tails, as we've written. The only problem in this argument is the sum of random variables we have here for this integral are not IID. So that kind of kills our idea of a central limit theorem because we do rely on independence. Okay, so the question is, can we somehow write this integral of this cam noise process as a sum of some random variables? Okay, maybe they're not completely independent, or at least they're kind of asymptotically independent. And so we'll actually divide this integral up into segments. So in some sense, this is an artificial division. It has no physical meaning. But what it will tell us is under what circumstances we expect to get a good approximation. Okay, so if we divide up this integral into pieces of length delta, then I'll call these capital Y's just these segments of the integral. And so this is basically saying if I take these segments sort of long enough but not too long, and I look at some statistical quantities, this is really what's called the cosum and the codifference, just two statistical quantities. If those quantities go to 0 for some value of delta, then that tells me, okay, over that length of delta, I should be at least getting close to some variables that are at least behaving in an uncorrelated way. And so here we see, and this is pretty typical of different parameter values, that both of these approach 0 as we get something like our delta is 5 or greater factor of epsilon. So it can't be as small as epsilon, but doesn't have to be orders of magnitude larger. Okay, so that gives us a little bit of confidence to proceed and still think in terms of the generalized central limit theorem for a sum of now these segments of this integral of the CAM noise process. Now the other problem we have is once we've done this, remember that these alpha stable processes have 3 different parameters that we need. One is, of course, the exponent for the tails. One tells us skewness, and one tells us scale properties. So in order to get the right fluctuations, we need all of those parameters. So we know the parameters for the CAM noise process for Y because that has power law tails. And so from that, we can actually get all of these other parameters. But we don't know them for these capital Y's. But we do have a linear relationship between the small y's and the capital Y's, basically through this integral and the linear behavior of Y. So we can derive that in sort of a messy way, but basically we can write the capital Y's in terms of let's say an initial Y in this segment with a bunch of coefficients. But the main, even without writing down the full expression here, the main thing to establish is a linear relationship. Because if we have a linear relationship between these variables, then we can write down we can borrow the parameters from the one density and use them in capital Y. And that gives us, at least for 2 of the parameters, the tail exponent and the skewness parameter, so the stability index and the skewness parameter, we can actually get those. And so this is just to use that linear relationship and compare using the stability parameter from the CAM noise process, so that's basically the tail exponent, and compare it to the capital Y process. So those agree well. So the red is the estimate, the black is the numerical piece. And for the skewness, the same thing. Again, we get a better approximation for skewness farther out in the tails than we do at the center of the distribution, which we'll see the effect of that a little bit later. Then the last piece is actually getting the scale factor. And so from that, we again use the central limit theorem type behavior and the behavior of the sum, and in fact the correlation, the characteristic function of this sum. Okay, and so we actually use kind of the form, this characteristic function as a Fourier transform, and use the fact that if I have a sum of essentially independent random variables, I can write down the behavior of the sum in terms of an asymptotic or a rescaled version of the characteristic function for the individual variables. It's still the problem shows that we still get a factor here. I've written it as capital sigma, which we cannot write down in closed form. Okay, we can actually show that both of these integrals, the integral of the CAM noise process and an integral of this Ornstein-Uhlenbeck-Levy process, that they both have alpha stable behavior, but there's a scale factor between the 2 that we need to find. Okay, and so if we would know, for example, the coefficients theta and sigma in the equation for Z here, the Ornstein-Uhlenbeck-Levy process, then up to a scaling factor, we would be able to find sigma. And similarly for and this shows up in the autocodifference or exponential behavior for that. So what we do is actually numerically estimate it from an empirical characteristic function. And once again, because we have characteristic functions, so basically looking at a Fourier transform or an exponential of our integral basically gives us a sum of a way to look at an empirical correlated, characteristic function, and using the scaling factors that go back and forth. So by computing this empirical characteristic function for the integral, then we can actually compare that and use that numerical factor essentially to go between the integral for the CAM noise process to this ratio of the terms for the Ornstein-Uhlenbeck-Levy process. Okay. So there is one numerical piece that we still have to do here, but it's relatively quick. Okay, so what that basically gives us, let's see if yeah, so basically that allows us to replace fluctuations in this y with fluctuations in the z for the Ornstein-Uhlenbeck-Levy process, because now we have all of the parameters for this alpha stable process. Now I just want to come back to remember we had to divide up this integral into these segments of length delta. And of course, if we're integrating this process over some time t, then delta is related to the number of terms that we have in this sum. And then we're back to this question of, we have this generalized centralized limit theorem. How large does n have to be? Right? So we had to take delta large enough so that n can't be too large, right? Because if n is too large, then delta goes to 0. But we'd like to have n large enough so that we get a reasonable central limit theorem type result.
What does it mean, large enough?
Yeah, so so I'm going to show that in a minute. But as we saw before, we needed delta to be, somewhere at least between 5 and 10, a factor of epsilon. So we needed to see that already. And so t is typically a characteristic long time scale that you would have separating y and x. So if I say that t has to be 10, then I need to make sure that, and I want to make sure n is, so and I'll say what large enough is. So I take my delta to be, let's say 10 times epsilon, then that gives me an n, okay? And then the n, we had this result earlier. I think it's coming up again on this, maybe the next slide. Yeah, here it is. So we have n to this convergence rate, which depends on alpha, okay? So if we want this convergence rate, that's basically saying how good is this approximation, the central limit theorem approximation. N has to be much larger if this convergence rate is close to 0. So if I get close to alpha is 2, then I'll see from this, if I want my error to be at a certain level, I'll have to take a very large n. Compared to if my alpha is around 1, then I won't have to take as many terms in this sum in order to get a good approximation. So it's all dictated by alpha. So it's a relationship between alpha and epsilon. And so depending on what my exponent is here for the CAM noise process, that will tell me how large n is, and delta will be dictated by the epsilon, which is the timescale separation. Okay, so that's something that we will see. Well, first let me just say again what we're doing, and then I'll show you the numerical simulation. So basically we're saying I have this system, the fast variable is forced by this CAM noise process, and now I'm replacing this CAM noise process with an Ornstein-Uhlenbeck process, and we had this averaging result earlier for a system that's being forced by Levy noise. And so we can get a new averaged equation in terms of x, so single equation with coefficients that really come out of this averaging result we had with Levy noise by replacing CAM noise with the effective Levy noise. Okay, so that gives us our new average system for this system forced by CAM noise. And here are the comparisons. So the main thing here is that the figures on the right are with a larger, alpha closer to 2. These are two different sort of nonlinear examples. And if you notice here, the red is the average case when epsilon is larger, and the blue is when epsilon is smaller. So if epsilon is smaller, then we have a chance to get a larger n, if you like, right? Because we can take delta a little bit smaller. That gives us a larger n, which means we can get a better central limit theorem type result. And so the approximations actually improve if we have the smaller epsilon, which is what we would expect. It's a small epsilon theory. And we see that that really depends on if alpha is how close it is to 2. So again, the figures on the right, we see more difference between the full system and the approximations, particularly if alpha is not so small. And that's really because we can't take a large enough n to get a good approximation for when we have this very slow convergence to alpha stable processes.
But there is no big difference between blue and red of this picture.
Actually, there's a pretty reasonable difference here, especially in the center, right? Because this solid line is the full result. The blue is the approximation, and red here you actually miss, especially in the centers. And I mean, we're still doing pretty careful approximations. In other problems, you will see much bigger variations depending on the system. Okay, so back to the original question: why do we expect to see these fat tail statistics showing up all over the place? And in particular, we see these in the multiple timescale systems. So when we look at these fluctuations around the mean, the case when we have these CAM noise processes, particularly with fat tail distributions, is usually there's kind of a balance between how strongly damped or how strongly attracting the system is to its mean. So if there's some weak damping with this CAM noise, then we typically get these alpha less than 2 tails. And so, but then if we look at these things over multiple time scales, the averaging kicks in, and we end up having essentially a Levy type noise or alpha stable noise that comes in through this averaging. But we also see that we have conditions under which this type of averaging actually occurs. So, you know, we have to have long enough time scales relative to this time scale separation. And in particularly, if we were on this boundary between sort of normal distributions and alpha stable distributions, then we need to see a much larger time scale separation to really get the alpha stable behavior. Okay, so maybe I'll just say there are a number of questions here we weren't totally thrilled with. We had hoped to get more explicit expressions for particularly some of the parameters and the densities. And also somewhere along the way, you know, there's still this question of how close these different densities are. And I don't really know much about this, but one way of looking at distances between densities is something called Stein's method, which may be another way to look at the differences between these CAM noise processes and these Levy noise type processes. And there's some recent results for non-Gaussian results for Stein's method, which has typically been used in normal distributions. So, and finally, thanks to the various funding sources, and thanks.
Question? situations with this heavy-tailed cam noise where you really would expect not to see alpha stable?
Yeah, so the I didn't say too many. I can just yeah, I didn't say a whole lot about this, but so this this exponent in the for the cam. So this is the attracting cam noise density. There's a nu here. That depends on all of these various coefficients that are in the cam noise. So depending on the combination of those, this exponent may be large or small, right? And so if this exponent is large, then you have something more like normal distributions. But if it's small, then you'll have more cam noise.
Hi, thanks for the talk. So in your derivation for the stochastic averaging for the cam noise, so when you had the integral of the cam noise and you represent it as a sum of IID random variables, I was wondering if the independence is actually a necessity. So maybe under some weakly dependent decomposition or some of weakly dependent random variables, if that would work.
It's possible. One thing we try to look at is trying to, I mean, I've done some other work in sums of random variables that are somehow correlated or have some relationship. And in those situations, we've been able to derive some other, expression for densities or whatever. In this case, it was just messy. And so we didn't do it. And also because we had this linear relationship, it wasn't necessary. But I mean, that was actually one of the first things we thought maybe we should do. And so there could be some results out there that could be useful like that.
And what are typical alpha in real life examples?
So in these, I don't remember exactly, but I think they're typically between 1 and 2 for a lot of the climate problems.
What is that?
I'd have to look in the papers to see exactly which numbers. I mean, I think I wrote down what it was for the ice core data. I think it was 1.7 or something like that. So, but it really depends on the particular model. That's like my third slide.
On model or on real life?
Well, oh yeah, I didn't write it down here. There are the statistical studies here. This is from ice core data, right? So I don't know if you consider that real life or not real life, but that's from data from ice cores and then doing the detrending and then doing the statistical analysis. So I didn't write down exactly what the exponent was, but they get some specific exponent there. And similarly with these models, so all of these papers here, they do the reduction, and then they will get a number for that exponent, right, depending on whatever system they've reduced.
Okay. That's accurate.
Thanks.